Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin, and I am the Technical Director at Micrographs Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off of your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once this session has concluded. I'm pleased to introduce today's speaker, Tony Thornton. Tony has more than 40 years of experience with micromeridics and in the field of material characterization. His expertise includes techniques for particle size, pore symmetry, physisorption, chemisorption, and pignometry. And Tony has contributed to the development of all of these techniques here at Micromeridics. Tony received both undergraduate and graduate degrees from Emory University. I have the pleasure of working with Tony for more than 20 years. He's a fellow of ASTM and recently honored with the ASTM Kavanaugh Award for his outstanding leadership and contributions to and the promotion of international standards development. Tony is currently Director of Technical Information at Micromeridics. Tony, it is an honor for me to introduce you today. We are so glad you could be here today to share your insights on AM Feedstock Powder and Particle Characterization, a more complete picture.
Jeff, thank you for that nice introduction, and thank you all for attending this webinar. There's been quite a bit of growth in the use of additive manufacturing, or AM, in place of more traditional means of fabricating parts. In some cases, part morphologies can be produced that were not possible with older methods. Many AM applications make use of powdered feedstocks, which include metal, ceramic, and polymeric powders. In a single production cycle, many parts may be produced, even of different shapes, but much of the initial feedstock remains in the 3D printer. Removing the remaining feedstock or replacing it is not economical in terms of powder cost, as well as disposal charges. It is far better to reuse than to refuse or discard. Of course, we must ask whether the feedstock has changed significantly by the printing cycle and whether it is still suitable for usage in another printing cycle. First, the important properties of the AM feedstocks need to be specified, and then test methods need to be documented to verify whether a lot of powder meets specifications. ASTM Committee F42 and ISO TC 261, working jointly, are developing specifications and test methods to do just that. Other ASTM and ISO committees are providing assistance and expertise. There have been many recent studies conducted to determine the powder flow and particle characteristics of AM feedstocks. Several of these have involved metal powders. Each involved characterization of fresh or virgin powders, along with powders that have been in the printer several cycles, what we refer to as used powder, and then blends of used and virgin powder, typically a 50-50 blend based upon mass. Today, we are presenting both bulk powder rheology and particle characterization analysis results. The study was originally conducted in support of a special interest program to be presented at the 2020 AMPM conference. The conference was canceled after the testing was complete. Results of the study, along with discussions, were published in Part 4 of Volume 56, Fall 2020, of the International Journal of Powder Metallurgy. SEM images were produced for the 4 powders characterized in the recent study. There were 2 containers of virgin powder, 1 container of powder that had been used for 8 print cycles, and 1 container of a 50-50 blend of virgin and used powder. 2 things are quickly apparent. First, there appear to be more fine particles present in the used and recycled feedstock powders. Also, there appears to be more agglomerated particles in these two feedstock samples. Let's keep these points in mind as we look at the results of powder rheology and particle characterization analyses. Let's start with powder rheology. Dynamic flow properties were determined using the FT4 from Freeman Technology, a division of Micrographs Instrument Corporation. These results are averages of triplicate testing performed at each of 3 independent laboratories. While there was some spread in results between the laboratories, similar trends were seen for most of the dynamic properties. Note that the aeration test results did not show differences that correlated well with powder usage history. The other flow parameters did, with some showing a large difference. These powders were sent to the 3 laboratories identified only as Powder A, Powder B, Powder C, and Powder D. It was only after results were submitted that the powders were identified. Powders B and D were the same virgin powder from the same lot. Powder A was from that same original lot of feedstock, but had been used for 8 cycles in the printer. Finally, Powder C was a 50-50 blend by mass of the virgin and used powder. Looking more closely, the basic flowability energy, BFE, is presented in the chart on the left. This is the energy required to move confined powder in a defined space. The higher the energy, the more resistance there is to confined flow. The BFE decreases significantly with usage. The powders flow better after being used. 2 things were noted when examining the SEM images. First, there appears to be more fine particles after usage. Second, there was more agglomeration present after usage. After looking at particle characterization results, a possible explanation for this behavior is offered. The specific energy, SE, is presented in the chart on the right. This is the energy required to move powder confined only by gravity. Again, there is a trend corresponding to powder usage, though the change is much less significant than for BFE. 2 additional dynamic properties are presented here: stability index, SI, on the left, and flow rate index, FRI, on the right. These are the ratios of BFE over a number of repeat cycles at the same flow rate for SI and at different flow rates for FRI. Both show small but consistent changes with feedstock usage. Bulk properties determined using the FT4 are shown in this table. Once again, each value is the average of triplicate tests performed at each of 3 independent laboratories. Trends are apparent for all 3. Note that there was quite a bit of variability in the compressibility results, and so the trend is not as statistically significant. The pressure drop of air flowing through the compacted bed of powder is shown on the left, with percent compressibility resulting from the compaction on the right. Though the used powder tends to compress slightly more than does the virgin powder, flow through the compacted bed is easier for the used powder. It is as if the powder offers less flow resistance. Maybe it is smoother on the surface. Here we see the first of the particle characterizations. These powders were also submitted blindly, this time with designations W through Z, so that they could not be matched up to those submitted for powder rheology until after the completion of testing. This time the virgin powder was submitted as powders W and Y, while the used powder was labeled as X and the 50-50 blend as Z. A Micrographs AccuPic 2 gas displacement pycnometer was used to determine the skeletal volume and density of a sample of each of the 4 powders. There's no significant difference in the skeletal densities determined for these 4 powders, indicating that there has been no significant change in chemistry nor significant contamination from powder usage. Note that the skeletal density is necessary for some of the other particle characterizations to be performed later. The particle size distribution of the 4 powder samples as determined using a Micrographs Sedigraph 3+ is shown here. This instrument determines a mass-based particle size distribution using X-ray monitoring of gravity sedimentation. The settling or sedimentation velocity is determined for particles and is equated to the velocity expected for a sphere of the same skeletal density. The diameter of that equivalent settling sphere is taken as the diameter of the particle under test. The sedimentation velocity is dependent on the friction between the settling particle and the liquid, a function of the particle size, the difference between the particle density and the liquid density, and the viscosity of the fluid. The median diameter, also called the D50, defined as the diameter corresponding to the 50th percentile of the cumulative mass finer than diameter distribution, as well as the diameter corresponding to the 10th percentile, D10, of the distribution, show a trend relating to powder usage history. It appears that the additional fine particles seen in the SEM images are detected in the sedimentation particle size distribution. The diameter corresponding to the 90th percentile, D90, shows a different trend, getting larger with particle usage. This is consistent with the appearance of more agglomerates in the used powder. Since these results are for a mass-based distribution, those larger agglomerates are massive enough to shift the D90 of the distribution, while there may also be enough of the fine particles present to shift the D50 and the D10 to smaller values. Let's take a closer look. Here we see the D10 in the chart on the left and the D50 or median diameter in the chart on the right. There are some differences that seem to align with appearance of fines in the used powders, but recall that these are summary statistics representing the entire distribution, and the agglomerates that appear do carry significant weight, especially for a mass-based distribution. The D90 results are shown on the left. We do see a definite increase in D90 for the used powder. The mass-based mean distribution, also known as D43, is shown on the right. Both show the influence of the larger agglomerates that appear to be in the used powder. Rather than simply look at summary statistics that don't focus on the tails of the distribution, those at the small diameter and large diameter extremes, ignoring what is outside the last 10% of the distribution, let's look at the full distribution. On the right, we see an overlay of mass-based incremental distribution determined for the four powders. Here we see what appears to be a wider distribution for the used powder as compared to the virgin powders, indicating an increase in both finer particles and larger agglomerates. The modal diameter, representing the maximum of the incremental distribution, is shown in the table and chart on the left. These tend to track with the increase in fine particles for the used powder. Air permeability analysis performed using a Micrographs sub-sieve autosizer 2 can provide a mean particle diameter but not a full particle size distribution, as well as an envelope-specific surface area. Resistance to flow through the compacted powder bed is related to the envelope surface area of the particles comprising the bed. Assuming a spherical model, a mean diameter can be determined from this envelope area. Skeletal density, previously discussed, is needed to determine the porosity of the compacted powder bed, a necessary value for the calculations. Neither the specific envelope surface area, shown in the chart on the left, nor the surface-based mean particle size, shown in the chart on the right, track with powder usage. It appears that neither the small increase in fines nor the small increase in agglomerates significantly impacted either of these particle characteristics. As previously mentioned, the bed porosity is needed when calculating the envelope surface area from air permeability, using the skeletal density and the dimensions of the compacted sample. Porosity can be calculated using the skeletal density from gas displacement and the conditioned bulk density from the powder rheometer analysis. Note that the bed porosities calculated using the two different techniques are similar, though not tracking consistently with powder usage. Adsorption of gas molecules as a function of gas pressure above the sample is used to determine the specific surface area for many materials and industries. One of the most common models used to determine the amount of gas molecules needed to form a single layer on the open surface of a sample under test was developed by Brunauer, Emmett, and Teller in 1938. Nitrogen is used most often as the adsorptive with the BET method, though other adsorptive gases are employed, often for particular applications. When the total amount of surface under test is low, krypton is usually selected as the adsorptive, as was the case with these metal powders analyzed using a Micrographs TriStar 2+, though any of our physisorption analyzers can be used for these analyses. Surface area is usually expressed as a function of mass under test. However, using skeletal density determined from gas displacement, the surface area can be expressed as a function of sample volume under test. Assuming a spherical particle shape, a mean particle diameter to account for the measured specific surface area can be determined. The particle size distribution determined using gravity sedimentation along with SEM images shown indicate an increase in the number of fine particles present in the used sample and an increase in the number of agglomerates. The fine particles perhaps were satellites removed from the surface of other particles, while the agglomerates formed by merging of two or more particles at basically point contacts. Neither of these processes is likely to change appreciably the number of gas molecules that adsorb into a single layer on the surface area of a test sample of these particles. This can be seen in the data shown in the two charts, specific surface area in the chart on the left and mean particle size on the right, where there does not seem to be any trend in values with powder history. We have seen that specific surface area can be determined using gas adsorption and air permeability, as well as calculated from the particle size distribution determined using gravity sedimentation by assuming a spherical shape for all particles of each size. Similarly, a surface-based mean particle size can be determined for each technique. For this study, we see similar values determined using the three techniques, though these do not seem to track necessarily with powder history. Even though specific surface area is not giving insight into changes that may be occurring with powder usage, at least through 8 printing cycles, the envelope surface of AEM powder feedstock is still significant, as that is where fusion of particles is taking place. Air permeability envelope surface area, as well as that calculated from sedimentation particle size distribution, are readily available ways to obtain a specific envelope surface area, though gas adsorption is by far the most used means to determine specific surface area of materials. Let's review the characterizations performed for these stainless steel AEM feedstock powders. First, we looked at determination of dynamic flow and bulk properties using the FT4 powder rheometer. Skeletal density by gas displacement analyzed using the AccuPick2 was later needed to complete several of the other analyses, as well as to provide information about the purity of the stainless steel alloy. Next discussed was gravity sedimentation particle size distribution determined using Sedigraph 3+. Then we reviewed mean particle size and specific envelope surface area determined from air permeability analyzed using the Subsieve Autosizer 2. Finally, the BET specific surface area was determined from krypton adsorption using a TriStar 2+. We saw that particle size statistics correlated well with the SEM images for the virgin, used, and 50-50 blend of virgin and used AEM feedstock powder, and did so for both the increase in fine particles seen as well as the agglomeration formed with usage. One of the most significant changes noted from the powder rheology analyses was that of the basic flowability energy. Most of the other dynamic properties showed trackable changes, as did some of the bulk properties. These indicate that the used powder was more flowable than the virgin powder, with the blend producing results between the other two. Often we see that the addition of fine particles will hinder flowability. Recall, though, we proposed that the increase in fine particles was the result of removal of satellites initially attached to larger particles, resulting in smoother particle surfaces. Smoother particles certainly promote better flow, and that seems dominant over the addition of the fine particles in terms of feedstock flow determined here. Since agglomerates of two particles tend to form a linear combination, there does not seem to be much impact on flowability with these particles. Remember, though, that agglomerates as well as fines may impact the quality of the printed part, and though not impacting flow, may still be significant when it comes to the use of recycled feedstock. The results of the sedimentation particle size analysis of these AEM feedstock powders did show evidence of increase in both the amount of fine particles and the amount of agglomerates in the used powder. While the summary statistics did indicate these changes, the extent is much more obvious from the plot of the full particle size distribution, as much of the impact is seen at the extremes of the distribution. The specific surface area determined using gas adsorption is based upon the normal of adsorptive molecules that form a single adsorbed layer about the sample. Agglomeration of particles and the removal of satellites result in small differences in the exposed surface area at such a molecular level, though remember that the particle surface is where fusion is occurring. The envelope surface area, though, should be affected to a greater degree with sedimentation and air permeability, as this impacts the way in which the fluid, liquid or air, flow about the particles. In short, both powder rheology and particle characterization provide insight into the quality of AM powdered feedstocks. All of these characteristics can assist with feedstock recycling strategies. Parts of acceptable quality were produced using all the powders investigated in the study, even after 8 printing cycles. The differences seen here may indicate what to expect with feedstock powders after more printing cycles. Future studies are planned to learn what happens after many more printing cycles, hopefully up to the point where the used feedstock no longer produces parts that meet specifications. It is expected that these characterization methods, both for the powders as well as the particles that constitute the powder, will provide information that could be used to detect problems before unacceptable parts are made, saving time and energy and thus money. I would like to thank you all for attending this webinar. Please stand by while we transition to the Q&A session after a short pause.
Thank you, Tony. I'm opening up the chat for everyone's questions now, and we already have a few. Tony, this is a really nice case study. Did you have to perform any special preparation of the materials before you tested them?
Jeff, that's a great question. Nothing really special. I mean, yes, there was some sample preparations done. For example, for the gas absorption analyses, there was some degassing performed. We degassed the powders at 200 degrees for a couple hours under flowing inert gas. For the sedimentation particle size analysis, the particles had to be dispersed in a liquid. It was one of our products, Sedisperse A13. We need a little bit higher viscosity for these larger particles, and there was a small amount of ultrasonication done with that. For the skeletal density determination by gas displacement pycnometry, we just purged the sample a few times with flowing helium to help remove any surface contaminations like water or whatever, and also to get rid of the atmospheric gases. The same sample preparation that was used for gas absorption was used for the subsieve autosizer, and then for the powder flow determinations using the FT4, basically the samples were handled with stainless steel containers, stainless steel spatulas, while the operators wore ground straps to try to prevent any kind of static. And there was some light mixing done for the powders before filling the containers. But pretty much, I mean, it was nothing special, just typical things that you do for all of these analysis techniques.
Just a quick follow-up question on that. How long does it take to perform these tests?
The powder rheology test, there's numerous samples done, depends on which ones you actually do, but maybe an hour and a half to get all of them complete for a set of samples. Cetograph analyses for particle size were very quick because these are large high-density materials. It only took about 2 or 3 minutes. About 10 minutes for the subsieve autosizer analyses. About half an hour for the gas displacement pycnometry. We did take the average of 10 analysis cycles on those. And then for the surface area analysis after degassing, about an hour and a half.
Okay. So someone asked, you know, for your case study, you use stainless steel as the material. Can these techniques be used for other chemistries? And are there any limitations for some of these other chemistries? So, you know, can we use them, you know, for titanium? Can we use it for different polymers?
Yeah, yes, it can. As a matter of fact, there's been some work, previous work done with what's called Ti-64 titanium that has a little bit of aluminum and vanadium added. That's been reported previously at one of the earlier AMPM conferences. There's been work done with polymers that have been published. I'm not exactly sure where those were wound up published, but similar work, although polymers generally can't be analyzed with the Cetograph. It's typically more for inorganic material, but all the other tests can be done. There is work starting with ceramic powders that are being mixed with binders and used in additive manufacturing. That is just getting started up. Recently, there's been a new joint working group in the joint ASTM ISO committee set up to deal with ceramic feedstocks.
Okay. We have a question about the FT4 test. Did you control moisture during the FT4 test, or was it just conducted under ambient conditions?
It was conducted in all three of the laboratories that did the work. It was conducted ambient conditions. I mean, these are, climate-controlled laboratories, so they tend to have relatively low moisture contents in the air, low relative humidities. But yes, nothing special was done during the analyses. These weren't done in a fume hood or in a glove box or anything like that. These were done just out in the laboratory.
So just to follow up on that, so do you think this is the way they were tested is typical, perhaps, of the way they might be used?
Sure. I mean, yeah, what goes on inside a 3D printer is going to depend, or the additive manufacturing device is going to depend a little bit on those, but those materials are going to be subjected to the atmosphere before being loaded in to the system. So, it's not that much unlike how they're going to be used.
And just to get back to the FT4 and the nice data you had from that case study, what were the really specific results from that demonstrated how clear, there was differences between new material, virgin material, used material, and blended material?
The thing that really stood out was that basic flowability energy, the BFE, which is, how much work is required to move the material to cause flow for a confined powder. And the powders became more flowable with usage. The used material had significantly lower BFE than the two virgin samples, and the blend fit in between those. We did see from the sedimentation and particle size analysis and from the SEM, we saw the presence of fines in the used material and in the blend, more so than what we saw with the virgins. And one working hypothesis on this, and we're trying to come up with a way of trying to confirm and prove that. One working hypothesis for that is that the fines that we see were satellites on the surface of the stainless steel particles that were used that became dislodged during either spreading or during printing or something. And the result is that the particles became smoother on the surface, more circular, if you will, after they were used, and as a result became a bit more flowable. We even saw a pressure drop, a lower pressure drop, a decrease in pressure drop in doing permeability studies with the used material having less pressure drop across the same thickness of a bed as the virgin materials. And again, it wasn't a huge drop, but there was a drop there. And even though the materials seemed to compact more, we wonder, is this an indication of the smoother particles after the analysis or after the usage of these materials?
Tony, we've got a question about the agglomeration, and
yeah, I see that.
I guess some of your previous discussions. Can you discuss a little bit? Just mention a little bit about a satellite with these materials versus agglomeration of the particles, and how perhaps these satellites may cause agglomeration and flow problems.
Yeah, when you have these satellites and you have a small particle on the surface of a large one, it causes them, it gives them places to interlock when they're trying to move past one another. When the surfaces are smoother, they can pass by one another much more simply. You maybe think of powder flow in similar way that you would think of viscosity in a fluid. And so the more cohesive the materials are, or the more that they tend to block and get locked on each other, the more energy is going to take to get these to flow. When you remove that satellite off of the particle, if that's what in fact happened to contribute to the finds that we saw, when that happens, you're going to have these particles able to move past one another much more easily. And even though you form an agglomerate, if you think about it, if only two particles happen to form that agglomerate, we didn't see much evidence of 3, 4, 5 particles sticking together. But if two particles happen to stick together, they're still linear. You got 2 points forming a straight line. And so they're not going to become that much rougher necessarily by doing so, especially if the particles that agglomerated to one another are of similar size. So we believe that we probably saw more dislodging of satellites than we saw new agglomerates forming. Because, and remember, when you're measuring this powder flow, you're measuring it for the entire powder bed, not for each individual particle.
Do you think these satellites can in any way influence interlocking of particles?
Usually when you have extra fines added in, there's more particles to bump against one another. They do fill in some of that empty space. But once the fines come off, apparently making the particles smoother contributed more to the overall flowability than adding in a few fine particles.
And we've got another question on what's been done to look at correlating FT4 with spreadability in powder bed fusion AM processes. Has there been any work done in that area?
There is. Things are being looked at in those areas in terms of trying to measure spreadability. There are some projects underway. There's a group within ASTM. It's the ASTM Additive Manufacturing Center of Excellence, and it has a group, an R&D group, where development of new techniques, new standards, new things to look at are proposed to them. There is some funding that is done, and then a small group is set up to look into that. And there are groups working on spreadability correlation, or measuring spreadability first of all, and then trying to correlate that in with powder flow. And then there's powder flow techniques other than just what we do with the powder rheometer, the FT4. There's other techniques for looking at flow that are being investigated as well. And all of this is trying to be pulled together to develop some sort of documentation in the form of ASTM and ISO standards to explain this, to give specifications for it, to define it, as well as to come up with techniques, standard test methods to determine it.
Okay. We've got another question here about the FT4 testing. Can you tell us a little bit about the maximum consolidation during that FT4 test for these materials?
There are some consolidation tests that can be done to measure a consolidation index. During this study, those were not conducted. To look at that, and basically looking at the consolidation with different amounts of, it's just essentially tapping can be done. There is a conditioned bulk densities that were measured, and we didn't see a lot of difference between those for this. That's after stirring the powder some and just measuring how much it compacts. We did look at compaction under force, and we saw small changes, 2 to 4% in the volume of the bed. We did not go look to see, where that would maximize, where that would hit a maximum with different amounts of force. I guess that could be done. We simply didn't look at it. It was not done as a part of this study.
Okay. Tony, any limitations on if we look at these materials? You showed surface area data by a couple of different techniques. Is there one of the methods that you looked at that seemed to have better agreement with what you were seeing from the FT4 with the powder rheometer? Because sometimes it's very difficult to have characterization data and then performance indicators. Sometimes that correlation is difficult to establish. Was there any one that appeared to be a better indicator or better agreement with the FT4 data?
Well, as far as surface area measurements went, one of the things that we noticed was that done by the traditional gas adsorption method to give a BET surface area did not show much differentiation. At least it couldn't be tied to the usage of the materials. One thing to point out there is that we are looking at determining the number of gas molecules it takes to form a single layer on the surface. And these processes of removing a satellite, if it weren't strongly held and to form an agglomerate, these things that we saw taking place, or we believe we saw taking place during the usage, those are not going to appreciably change the number of gas molecules it takes to form a single layer on the surface. So we did not expect necessarily to see a large difference in the surface area by gas adsorption, but we wanted to test that. And when we didn't see a huge difference, it wasn't surprising. That calculated from the particle size distribution that we got from sedimentation, we did see some possible indications in that when you, with that technique, you're looking at an envelope area. And so as liquid flows around it, if there is, say, a satellite sitting on a larger particle, there is going to be, significant more surface friction than there is going to be if you remove that satellite. So we do think we saw a little bit in there. It was not as significant as the powder flow data that we saw, but we did think that from the particle size distribution, since we did see presence of fines, that we probably saw more, a little bit higher surface area after removing fines from the surface of the particles. With the agglomeration, we did not see much going on there, because if you take two particles that are settling through a liquid and you put them together, you didn't change their envelope surface area very much. Realize also that we're looking at calculated values covering the total range of particles. We had two things working against each other. More fine particles may be increasing the surface area a little bit by coming off the surface of the other ones. More agglomerates forming, maybe decreasing the surface area a little bit. So since they're working against each other, there may be some canceling going on there. We just simply don't see that type of definition like we do from the powder flow tests. One other thing is the subsieve autosizer only gives us an average size, but it does give a size based upon an envelope surface area as well. Since we have air flowing through the packed bed of particles, again, that is going to be an envelope surface area phenomenon, much like what we would see from particle size determination by gravity sedimentation. And we did see reasonably close agreement between the surface area measured by all three techniques, but especially between that from the Sedigraph and that from the subsieve autosizer, since they are dependent on envelope surface areas. So because of the fact we're taking a single measurement, if you will, for an entire bed of material, maybe there is some canceling, agglomeration effects, canceling a little bit of what we see with the finer distribution. One of the things the Sedigraph showed us is the distribution got wider. It increased the amount of fines and the amount of larger particles.
From the particle size data and your really nice FT4 data, the powder rheometry data, do you think, well, it seems as though you're seeing some clear differences when you look at the flow energy that really define these materials much better than what we were able to see from simple characterization. Is there an advantage of using the multiple techniques for looking at these materials?
Oh, absolutely. I mean, we see a change in the flow. We want to know why it happened. And what the particle size distribution analyses gave for us is some possible explanations because of the presence of more fine particles, because of a few agglomerates showing up. It did help us to try to say, okay, why is it we got higher flow? Why do we have higher flow rates? Why is it easier for these particles to flow? So again, they support each other. That's why we do these different techniques. We wanted to see, was there any change in the chemistry of the materials? That's why we did the skeletal density determinations. We didn't see contamination coming in. We didn't see a significant change there. We looked at surface area. We looked at particle size distribution by a couple of different techniques. So again, the idea was, let's try to find some supporting evidence for why we're getting a difference in flow.
At the end, you touched upon briefly on the number of cycles or passes some of this material may be used for. And I think that number was around 8, but you also indicated there were some other significant concerns about the quality of the product after having used the material multiple times. Is there anything you saw in your data that would be some indicators as to when the material may no longer be suitable?
Through the completion of 8 cycles, what we saw was that, well, first of all 8 cycles produced good parts. Even when they went back and created some parts with a blend, they produced good parts that met the quality specifications for the part. So for the parts that were being made using these materials by powder bed fusion using a laser beam, good parts were being produced. They met specification. That's the one important factor right there. There have been some studies where materials that have been used in longer numbers of cycles, up to about 30, that they're starting to do some work with those, and it's still they were producing pretty good parts at the end of 30 cycles. There is a study underway through one of the joint working groups within the additive manufacturing ASTM and ISO committees. There's a project being done by the Additive Manufacturing Center of Excellence to look at going upwards of maybe even 80 to 90 cycles. And there are some things that are starting to be seen there. The project is still underway. And so we don't have full set of data yet, but there were some product defects starting to show up. This group is working on developing recycling strategies, and we are actually currently writing standard practices for ASTM standards as well as ISO standards on standard practices for recycling philosophies or recycling schemes for both powdered metal and right now polymeric feedstocks. We haven't started with ceramic ones yet. So that work is being done, but imagine the amount of work it takes to use powder. They do have to replenish it slightly with a little bit of virgin powder sometimes to make sure there's enough, but to go through 80 or 90 print cycles. So that's a bit detailed work. Now, what are we seeing? We're seeing some of the things that can happen, the formation of more fines, the formation of agglomerates. We're seeing those after 8 cycles. It has not gotten bad enough yet to start making bad parts, but we don't want to start making bad parts because that wastes time and energy, which means it's wasting money. So yes, we're doing these studies ahead of time to try to see what are the early predictors that can come into play, that maybe some modeling can be done to try to decide, okay, this is going to lead to a problem. Yeah, we'll do a few tests to see where those problems occur and when they occur and how they occur. But we definitely want to make sure that our strategies that we publish for reusing materials make sure that if you follow this technique, you're probably guaranteed to have pretty good parts throughout the process. Yeah, you have to do a little bit of testing. Here's how you can do those tests. But let's develop a strategy that'll work without wasting a lot of money.
All right, that's all the questions we have time for today. If we haven't been able to get to your question, one of our application team will be in touch shortly. Tony, is there anything else you'd like to mention today?
No, not that we haven't covered. Just let everyone know that, you know, these things are being developed. These things are being worked on. This is not the end of the process. We are definitely going to continue work in these areas. Come back, check back with us. Stay tuned. There will be either publications done like this or publications done elsewhere because the work is just beginning. And I just want to say thank you to everyone for attending today.
Great. Tony, thanks for that really nice case study looking at these different measurements and methods for evaluating these materials. Thank you, everyone, for participating in today's webinar. If you have any feedback for us, we would be grateful if you could complete the survey, which will be distributed in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again very soon. Thank you and have a nice day.